Hello and welcome back to the deep dive. I am absolutely buzzing with energy today because we are tackling a subject that feels like it's straight out of a sci-fi novel.
Right.
But it's actually one of the most critical logistical feats in the modern world. Usually, when we talk about fuel, we're talking about burning things, heat, fire, combustion. But today we're talking about the complete opposite. We're talking about freezing things. We're diving into physics that feel almost backward.
It is a completely different beast, isn't it? It challenges your intuition at almost every turn.
It really does. But before we get into the mind-bending science of it all, I want to send a massive warm welcome to our OSSA LNG listeners.
Absolutely.
It is fantastic to have you with us for this one. I know this is your bread and butter, so we're going to do our best to do the science justice.
Welcome to the OSA LNG crew. It's great to have experts listening in.
And hey, if you are new here or if you're part of the OSSA crew tuning in for the first time, do me a huge favor and smash that subscribe button on the channel. We're dropping deep insights like this regularly and you do not want to miss out.
Please do.
So here's the mission for today. We have a stack of technical manuals, safety protocols, and physics papers in front of us, and we're going to unpack the reality of liquefied natural gas, LNG. And the more I read, the more I realize this isn't just fuel. This is a high-stakes battle against thermodynamics.
That is the best way to put it. The average person thinks of gas as a utility. You flick a switch, the stove turns on. Simple.
Right.
But when you're transporting it as LNG, you are dealing with a living cargo.
A living cargo.
It's dynamic. It changes chemically while it's sitting in the tank. It can freeze steel until it shatters like glass. And if you handle it wrong, it can create its own weather.
Wow.
It requires a level of precision that makes, standard oil shipping look almost casual by comparison.
I love that image. Okay, so let's start there with what? We know it's gas, but we've done something fairly extreme to it to get it onto a ship. What is that transformation?
We've subjected it to a massive liquefaction process to turn natural gas into a liquid. We're not just cooling it down a little.
Not like putting a soda in the fridge.
Exactly. We're removing the sensible heat, that's the temperature drop, and the latent heat. And that's the real energy it takes to actually change its state from gas to liquid.
And why? Why go through all that trouble?
It's all about one magic number, 600.
600.
Approximately. When natural gas turns to liquid, it shrinks. Its volume reduces by a factor of about 600.
So you're saying if I had a room filled with 600 beach balls.
Yeah, a whole warehouse of them.
You could squeeze all that air into the size of just one beach ball.
That is the density we're achieving. That is why the industry exists. Without that compression, shipping gas across the ocean would be, commercially impossible. You just couldn't carry enough energy.
That is incredible. So physically, if I'm looking at a sample of this, safely, of course, what am I seeing?
It's actually disappointingly boring to look at.
Really?
It looks exactly like water. Clear, colorless, odorless.
Yeah.
But do not be fooled. If you touched it, you'd lose your hand instantly.
Right.
It's stored at its boiling point, which is roughly minus 160 degrees Celsius to minus 161.5.
Minus 160. That's colder than anywhere on Earth ever.
Pretty much.
And is it just pure methane?
Primarily, yes. Mostly methane, CH4. But it's actually a cocktail. It has traces of heavier hydrocarbons.
Like what?
We're talking ethane, propane, butane, maybe some pentane. It all depends on where it was drilled.
Okay, so it's a mix. And I saw something in the data sheets that surprised me. Despite being so dense in energy physically, it's actually light.
Very light. Its density is about 426 kilograms per cubic meter. For context, fresh water is 1,000.
So it's less than half the weight of water.
Less than half. If you poured it onto water, it would float right on top, like oil.
Okay, hold that thought on pouring it into a swimming pool, because I definitely want to unpack that. But first, you called it a living cargo. You said it changes while it travels.
Right. This is the concept of aging. And it's a fascinating problem for the engineers on board.
I usually associate aging with, fine wine or cheese, not industrial fuel.
It's a bit less romantic, but the chemistry is similar in that the profile changes. See, the ship's tanks are basically giant thermos flasks, but no insulation is perfect.
Heat is always going to find a way in.
Exactly. You're sailing through warm oceans, maybe 20, 30 degrees Celsius, and the cargo is minus 160. That heat gets in and causes a small amount of the liquid to boil.
And that's the boil off.
That's the boil off. But here's the catch. Not all components in that cocktail boil at the same temperature. Nitrogen and methane are the lighter ones. They have the lowest boiling points. What do you think happens?
They boil off first.
They boil off first.
So it's like if you boiled a pot of soup, the water leaves, but the heavy ingredients, they stay behind.
That is a great analogy. As the voyage goes on, you're losing methane and nitrogen gas. This means the liquid left in the tank gets richer in the heavy stuff, the ethane, propane, and butane.
So the fuel you discharge at the end of the trip is chemically different from what you loaded?
Precisely. It's aged, it is denser, it's actually slightly hotter, and crucially, it burns differently because its caloric value, the energy it holds, has changed.
That is a wild variable to manage. You're not just navigating the ocean, you're navigating the changing chemistry in your own tanks.
Keeps you on your toes.
Speaking of things that keep you on your toes, let's talk about the big one, flammability. How do we keep this massive amount of potential energy from going off?
Well, this is where we have to get technical about the flammability triangle. Methane doesn't just burn anytime you light a match.
It has rules.
It has very specific rules. In a normal atmosphere, which is about 21% oxygen, methane will only burn if its concentration is between roughly 5.3% and 14% by volume.
That seems like a pretty narrow window.
It is. Below 5.3%, it's too lean. Not enough fuel. Above 14%, it's too rich. Not enough oxygen. But inside that range,
that's the danger zone.
That's where things go boom.
I was looking at this diagram in the source material, this triangle chart. It looks like a navigation map.
It essentially is. It's a navigation map for chemistry. Imagine a triangle. One corner is 100% oxygen, one is 100% methane, and one is 100% nitrogen. There's a forbidden zone in the middle where the mixture is explosive.
Right.
Our entire safety protocol is based on plotting a course around that zone so we never ever touch it.
So if you have a tank full of air, you can't just pump methane in.
No, absolutely not. If you do that, you go from 0% methane to 100%, and on that journey, you will cross through the 5% to 14% range. You're driving right through the minefield.
So how do you cheat the system? How do you get from air to methane without crossing that line?
You take a detour, you use a bridge, and that bridge is nitrogen. We call it inerting. Before we put any methane into a tank, we flush the air out with nitrogen. We keep flushing until the oxygen level drops below 2%.
Why 2% specifically?
Well, theoretically, an explosion can't happen if the oxygen is below about 13%.
Okay, so that's the hard limit.
That's the scientific limit. But in the LNG world, we do not mess around with theoretical limits when lives are at stake. We drive it down to practically zero. So 2% or less.
So you remove the oxygen first. You push the mixture down to the bottom of that graph.
Correct. You go from air to nitrogen. Then once the tank is inert, you introduce the methane. You move across the bottom of the graph. You move tangentially to the danger zone. You skirt right around the edge of it.
That is such a cool visualization. You are literally navigating around an explosion using chemistry.
It's the golden rule. Never let methane and oxygen meet without nitrogen acting as a chaperone.
Now let's talk about when things go physically wrong. The swimming pool scenario. If LNG spills, say, onto the water, what happens?
Drama. Pure physics drama. The LNG is minus 160. The water, even if it's freezing, is still what? Plus 1 or 2 degrees.
To the LNG, that water is a frying pan.
Exactly. It boils violently. We're talking rapid boiling. And it's so turbulent that no coherent ice layer can even form on the water. It just churns.
And this creates the famous white cloud.
It does. But that cloud is a very common misconception.
Oh, yeah.
Methane vapor itself is invisible. You can't see it. The white cloud you're seeing is actually fog.
So it's moisture from the air condensing.
Exactly. The vapor is so cold it just freezes the humidity right out of the air.
But it's a useful fog, right? It's a warning.
Extremely useful. Generally speaking, the flammable range, that danger zone, is contained inside that white cloud. If you are standing in the fog, you are in the danger zone.
Got it. Okay, but there was one warning in the safety protocols that really stuck out to me because it felt so counterintuitive. It was about drip trays.
Ah, yes. The RPT risk, rapid phase transition. This is critical.
The manual said if LNG spills into a containment tray, you must never direct a water jet into it. My instinct is to grab a hose and wash it away. Why is that the wrong move?
Because this is a life-saving detail. If you shoot a jet of water into a pool of LNG, you are injecting a massive amount of heat instantly.
Okay.
This causes that rapid phase transition. The liquid expands into gas so fast, we're talking milliseconds, that it creates a physical explosion.
Not a fire, a physical explosion.
Pressure explosion, yeah. The liquid expands 600 times in volume in the blink of an eye. It's like a bomb going off.
Yeah.
You'll blast LNG and ice particles outward like shrapnel.
So you turn the drip tray into a grenade.
That's exactly what you do.
That is terrifying. So what is the correct action?
You have to fight your instincts. You let it boil off naturally. Or you must use water. You spray the sides or the base of the tray to warm it gently. You never, ever touch the liquid surface with a water jet.
That is the kind of insight I love. Something that saves you from a disaster you didn't even know you were causing.
It's all about understanding the physics. Standard procedures don't always apply to cryogenics.
And speaking of cryogenics, what does it do to the ship itself? This brings us to material science.
This connects back to that shattering like glass image. This is about the ductile to brittle transition.
Explain that.
Most normal metals, like the mild carbon steel used for, say, a standard ship hull, have a personality change when they get cold.
A personality change.
At normal temperatures, steel is ductile. It can stretch and bend a bit, but somewhere between minus 50 and plus 30 degrees Celsius, it goes through a transition. It becomes brittle.
And LNG is at minus 160.
Way, way below that limit. If liquid LNG spills onto a standard steel deck, the steel undergoes massive thermal shock. It tries to contract from the cold, but because it's now brittle, it can't stretch. So it fails.
It cracks.
It doesn't just crack, it fractures. We're talking about the solid steel deck of a ship shattering like a dropped dinner plate.
Catastrophic. So the tanks can't be made of that.
They're not. We use special alloys that don't have that brittle transition. We use materials like Invar, which is a 36% nickel iron alloy, or austenitic stainless steel, or 9% nickel steel.
I saw aluminium alloys on the list too.
Yes, specific ones. They're expensive, hard to work with, but they're the only things that can hold the cold.
Okay, so the tanks are safe, but the deck is still normal steel. So back to the spill. We just said don't use water in the drip tray. What about on the deck?
And here's where we flip the script again.
Okay.
This is why you have to understand the why. If it spills on the deck, you must flood the area with water immediately.
Wait, really? Flood it?
Yes. You need to use the water as a heat source.
Water as a heater? That just sounds wrong.
It does. But remember the temperature difference. To the steel deck, that water is like a warm bath preventing hypothermia. By flooding the deck, you disperse the LNG, yes. But more importantly, you warm the steel. You keep the steel above that brittle transition temperature so it doesn't shatter.
That is wild. So water in a confined tray of LNG equals a pressure bomb. Water on an open deck with LNG equals a safety blanket.
Correct. You have to know which problem you're solving. Expansion pressure or thermal shock. The answer changes the protocol entirely.
That requires some serious situational awareness.
Autopilot gets you killed in this industry. And we haven't even touched on the silent killers yet.
Right, the inert gas, the nitrogen we use is that bridge. The source material calls them silent hazards.
They are asphyxiants. Simple as that. Nitrogen is a pure gas. Inert gas, which is generated on board, is mostly nitrogen and CO2 with less than 2.5% oxygen.
And the risk is that you can't tell they're there.
Exactly. Domestic gas in your kitchen has an odorant added, that rotten egg smell.
Right, that's artificial.
It's put there on purpose.
Right.
But on an LNG ship, the gases are odorless. Methane is odorless. Nitrogen is odorless. You can walk into a space, feel absolutely fine, take a breath, and just drop dead because there's no oxygen.
You don't even cough or gag.
Nothing. The lights just go out.
So you rely entirely on sensors.
You have to. But, and this is a huge but, you have to know how your sensor works. The sources point out a very specific detail here.
Is this about the catalytic sensors?
Yes. A standard portable gas detector often uses a catalytic sensor. It works by, well, it actually burns a tiny sample of the gas inside the sensor.
Okay.
To burn something, what do you need?
Oxygen.
Exactly. So if you're trying to measure methane inside a tank that's full of nitrogen, there's no oxygen. The sensor can't burn the sample. So what does the sensor read?
0.
It reads 0, even if the tank is 100% methane.
Wow. So you could be standing in a tank full of fuel, look at your meter, see 0, and think you're safe.
Precisely. That is why the manual specifies you must use special infrared instruments to measure methane in nitrogen atmospheres. They work by light absorption. They don't need oxygen. They just see the gas.
It really seems like every single step requires you to be awake and questioning your assumptions. You can't just follow a checklist.
That is the essence of it. It's knowledge applied in real time, whether it's the brittleness of steel, the boiling curve of the liquid, or the type of sensor in your hand.
So let's wrap this up. We've covered the transformation to liquid, the aging cargo, navigating the flammability map, the physics of spills, and the material science. What's the big takeaway here?
I think it's about respect. We are harnessing a massive energy source, but to do it safely, we have to respect the physics. We have to understand that cold isn't just a temperature. It's a state that changes the integrity of the world around it.
And that's what I love about these deep dives. Shipping gas isn't just logistics, it's a high-stakes science laboratory floating on the ocean.
Absolutely. And for the crews operating these vessels, it's about discipline. They're managing a cargo that wants to boil in a ship that wants to freeze, surrounded by an ocean that acts as a giant heat source. It is a brilliant balancing act.
A brilliant balancing act indeed. Well, to our OSA LNG listeners and everyone else tuning in, I hope this gave you a new appreciation for what's happening inside those tankers. Thank you for trusting us to dive into your world.
It was a pleasure. Stay critical. Don't just look at the reading on the dial. Understand how the sensor works.
Love that advice. And one last reminder, if you enjoyed this, please hit that subscribe button. It helps us keep the lights on and the insights coming. Stay curious, stay safe, and we'll catch you on the next deep dive.